Okay,
Let me
great.
share.
Yeah, so our next speaker is John Nolan, and he's going to tell us about symmetric monoidal categories with attributes.
All right. Hi, everyone. My name is John Nolan. I did this work while at the University of Maryland, though right now I'm in between institutions. I'm going to be starting graduate school at the University of California, Berkeley in the fall. Most of this work was done in conjunction with Spencer Breiner of the National Institute of Standards and Technology in the US. And so this is kind of a special categorical component of some larger robotics-based project that we're all working on, trying to figure out how to use string diagrams and the like to model processes and plans in robotics. So without further ado, first we gotta wonder what we can really get out of applying category theory to robotics. So one major component, a lot of these are discussed in a forthcoming paper by Angeline Aguinaldo, Archimedes Canedo, and William Regley. So one major thing is that when you're programming robots, you have to consider a lot of interactions between different domains and levels of complexity. For example, you can have stuff going on a Boolean level where it's very much describing propositions about the state the world is in. You could also have things on a lower level geometric level where you're all considering configurations of your robot in R3. And so category theory helps you connect all these different contexts together using functors and whatnot. There's also the fact that the string diagram calculus is a little easier to read and work with than traditional specifications. So that can help people who aren't experts in robotics get involved in the process and have some ability to influence the planning of things that they have a stake in. So just to go through this string diagram right here, we're going to be reading string diagrams from top to bottom. This gives a basic plan for a robot to pick up a ball. So we start out with a robot object and a ball object, and then we somehow figure out the location that the ball is in. We tell the robot to move to that location, and then we tell the robot to pick up the ball, and we end up with a robot holding a ball. So one nice thing about this whole string diagram formalism is that, as those of you who've submitted a paper to this conference can probably attest, they make it a lot easier to prove things about what's going on in these symmetric monoidal categories. So, for example, here we have this big plan that you start with a robot, a ball, and a goal, and you want to end up getting the ball to the goal and you're going to end up using the robot to do so. So we start with this whole plan of having the robot move to the ball's location, pick up the ball, move to the goal, and then place the ball down. And just starting from reflexivity of this, we can add some more on because we can copy the location of the goal into two different values, and then we have this one go into the move to, and this one dangles off for a little bit. And then based on an axiom we can define for the move to operation, we can end up using this right here to check that the robot ends up in that after the robot moves to the specified location, the position it ends up in is in fact the position we told it to go to. And similarly for this place, we can check that when we have it place the ball down, the place the ball ends up in is the place the robot was in when it put the ball down. So some questions you might have about this formalism that I've just been showing off. Why are these dashed lines different than the solid lines? What makes them quite so? Why do we even use a different thing to write them down? And loosely speaking, this is because the dashed lines here are meant to represent information or values, while these solid lines are meant to represent physical objects, or entities, as we'll call them. Another question you might have is, what are these circles and triangles? We keep showing them, and you might have gotten some intuition for them from the previous slides, but you probably don't know the formalism for them yet. And how are they supposed to behave? How can we expect them to work axiomatically? So for the first question, we're going to borrow the notion of a data service from the paper Monoidal Computer 1 by Pavlovich. And a data service inside of a symmetric monoidal category is a general formalization for ways you might want to process data. And it's an algebraic structure together with a multiplication that intuitively serves as a filtering for equality. So we take in two values right here, and then we check whether or not those values are equal. If they are equal, then we spit out the common value. If they are not equal, then we end up breaking. We say, this plan doesn't work. There's a co-multiplication that copies out the value you put in. So you take one value and you come out with two copies of the same value. And there's a co-unit, which you put in a value and then you just forget about it. And these are supposed to satisfy axioms that are similar to those of a special commutative Frobenius algebra. And in fact, a data service is just, for those in the know, a data service is a special commutative Frobenius algebra, except for the fact that we don't require the multiplication to be unital. And this all ties into one grounding application being to the category of sets and partial functions, in which every object has a natural data service structure, or maybe I shouldn't say natural because that's a bit of a technical term in category theory, but every object has a canonical data service structure, but this is typically not unital. So to understand these triangles, we have to figure out how we want to attach values to entities. So for example, and we do it through an action of the data service on the underlying entity, which all the information we could want out of that is contained in a comonoid action from the underlying entity to the entity tensored with the data service. So for example, a robot to a robot and a location. And this basically serves as just getting out the location from the robot without really doing anything. And the axioms, the comonoid action axioms for this are basically saying that if you get out the location of a robot and then you get the location of the robot again, that's the same as if you had just gotten the location once and then copied it. Same thing for other attributes. In some sense, if we view this gamma map as somewhat like the get of a lens, then this is somewhat like a get law, which doesn't normally arise in the context of lenses, but might be necessary for a resource sensitive understanding of lenses. And it's interesting to note that this notion arose earlier in a talk today on the Safari of update structures. So seems like it might be somewhat important to a broader understanding. And this axiom right here, which says that if we get out the attribute and then we just delete, and that's the same as if we had done nothing. So really, this gamma map is purely an informational action. So given this gamma map, just like how we can check values for equality, we can also check that an entity or a pair of entities has a certain attribute. So this phi map defined right here, if we take M to be a robot and D to be a location, then this is checking that the robot is at a specified location, and it can be formally defined using this. And this checks that two objects have the same value for a given attribute. So, for example, checking that a robot and a ball are both at the same location. So we can compile this all into the titular definition of a symmetric monoidal category with attributes. We take a symmetric monoidal category. We can construct a category of data services within that symmetric monoidal category. And that's defined inside of our paper. You can see that for more details. And an attribute structure consists of a category of attributes, a functor sending, so each object in this category is going to be an attribute, and the morphisms govern how the attributes connect to each other. A functor sending each attribute to its underlying entity, and another functor sending each attribute to its underlying value, and a natural transformation connecting entities and tensor products of entities and values, such that each component of this natural transformation is a comonoid action. And so the reason we consider a whole category of attributes is because we often want to consider situations where we have multiple interacting attributes. So although we've just been talking about robots and locations, we could also want to talk about robots and charges, robots and colors, all sorts of different attributes at the same time. And so you might be wondering why this, you might have followed most of the previous definition, but still be wondering why these gamma maps are supposed to be natural. And the reason for this is that morphisms like this move to right here are going to have effects on the attributes. So for example, this right here tells us that if you move to a location, then the location you end up at is the location you move to. And we should be able to, in some way, predict how these morphisms are going to affect the attributes in question. And this can all be tied up into a naturality condition on these maps. I should note that this is just a normal attribute of a robot. This is, we can view the co-multiplication of a data service as being a data service action on itself. So in that sense, this gives rise to the attribute that's in the domain of this process. So to formalize the example we've started off with, we can consider a symmetric monoidal category which is generated by a location, a robot, a ball, and a robot holding a ball. And the generator morphisms are a data service structure on the location, as well as morphisms letting us move the robot to a location, move a robot holding a ball to a location, have the robot pick up a ball, and have a robot holding a ball place the ball down. And the point of the attribute structure that we've been talking about is that it allows us to impose all these equations following a given structure and tell how these move to, pick, and place actions are going to affect the underlying location of their domains. So we can also augment this a little by enriching in the category of posets. One of the key examples to keep in mind, and that we've kept in mind, is the category of sets and partial functions, which has a standard partial order on the Hom sets, giving a poset enrichment, where one morphism is less than or equal to another, if and only if the latter morphism is an extension of the former. So the latter has a larger domain and agrees with the former whenever the former is defined. And so in general, we can take this as a syntactic way to formalize the notion of partial definition of one morphism ending up producing valid results less often or less than or equal to as often as another. So we can implement this within our framework by making every category and functor involved into a Poset-enriched category, and by adding some extra conditions on the data services and morphisms involved. This is all somewhat motivated by how monoids and other objects are supposed to behave in the category of sets and relations. You can see the axioms for this that we ended up using for this all appeared in a paper by Bonci, Pavlovich, and Sobochinsky, dealing with Frobenius algebras in the category of relations. So one of the example inequations that we require to hold is that if you take two data services and you filter them for equality, and then you copy the result, that always gives you the same results as just doing nothing to the two input values whenever this one is defined. But this one is typically going to be much less frequently defined than just doing nothing. So we've also done some work on considering the semantics of categories with attributes. So two main types are described and outlined in the paper. There's a Boolean context, which relates to this thing called the planning domain definition language, which is used a lot in plan-based artificial intelligence. And there's a geometric context, which relates to the canonical robot command language, which is a much lower level language, and can be used to describe how robots should act in order to accomplish a goal. So the PDDL specification might be something high level, like tell the robot to move to this location, whereas the CRCL specification would be something like tell the robot to rotate its arm joint by 30 degrees in this direction. And we're still hoping to implement this in more practical cases, but we have an idea for how the general workflow of the connection between our syntax and these various semantics would go. You would start off by creating some sort of description of the problem you want to consider within PDDL, and then you could interconvert between that and the string diagram formalism, both of which are higher level approaches. And then you could, in some way, take a string diagram you have and end up compiling it down into CRCL and getting the low-level commands that tell the robot to do what you want it to do. So overall, the messages of this talk are that string diagrams can help you make planning in robotics and other fields of engineering a lot clearer and more accessible to people who aren't maybe trained in formal engineering. Category theory can also help connect these different semantics, the Boolean and the geometric semantics, which were just mentioned. And this whole research project is still developing, it's ongoing. There's still a lot to be discovered and implemented. So if you're interested in studying this in greater depth, I encourage you to contact myself or Spencer. Our contact info is right here. And thank you all.
Okay, thanks so much. This sounds really exciting. So yeah, we have 5 minutes for questions. Please speak up.
I can ask a question.
Yeah.
So if you move your robot to A and then you move the robot to B, is that the same thing as first asking if A and B are equal and then moving the robot to that location, or did I miss something?
I think I might have. That's not the same.
Like,
that's meant to be.
Yeah.
That's meant to be what you'd. It should be what you would expect it to be from just outside of this categorical formalism where you tell the robot to move to a location and then you have the robot move to one location and then go to the other.
Okay, I thought I saw a relation that was like first comparing them as mono, and yeah, I don't see the screen, but that's great. Okay.
More questions?
I have a question.
You can ask.
Okay. Right, so I think this is very interesting. My question is whether or not you've considered and have any examples of situations in which there are two categories and each one sort of defines an attribute structure on the other.
Yeah, I don't think we've thought of that at any real level, but that would be an interesting thing to consider. We've mostly been constrained to more practical questions of how do we define models for robotics so far.
Okay, thank you.
So, hi. My question is one about, for instance, at slide 9 on the move to. So you move to a location, but you never actually quite get to that location, right? So you wanted to move to an L, but really you might get to like an L prime that's really close. How does that sort of scenario fit in with your model?
Yeah, so if we're talking about the if we're talking about the Boolean semantics, then most of the way Boolean semantics are written out is this very coarse notion of you're moving from one room to another. So in that case, you don't have any of this complexity. But that is a good point. If you're working in a more finely grained setup, then you would want to have some sort of fuzzy notion of comparison.
And is that something that you would have to extend this with, or does that already fit in the framework as is?
We'd probably have to extend it in some way.
Okay.
At least an extension on the semantics we've presented so far.
All right, thank you.
Maybe we have time for one more quick question if there is one.
Yeah. What about kind of cost semantics, where each action has a different amount of cost in terms of energy or time? Is that something that would make sense?
Yeah, so one of the examples I mentioned before is, for example, considering the charger robot. So you might have to have a robot with a specific charge in order to perform some sort of action.
Oh, okay.
We're still kind of working on figuring out how to properly incorporate time into the formalism, since pretty much every real physical action would necessarily take on some time. So we'd have to figure out some good way to keep track of that, but
Mm-hmm.
Yep.
Thank you.
Okay, so let's thank John again.